Hi guys, this is our last lesson for the finite square of potential, and let's see how we can calculate the discrete energy values. So where we left off is we had these two equations over here and we need to solve them. When we solve for K1 and K2, we get energy values because K1 and K2 is given by that over there. As you can see, the energy value, by solving K1 and K2, we can rearrange for the energy values. Now this equation, we get it from applying the boundary conditions for the antimetric solution and the symmetric solution. We also mentioned that we can't seek out an analytical solution to this equations over here. Instead, we need to employ some of these graphical mathematical methods. Now, if you got a modeling software or maybe a graphing calculator, maybe you could just use the software and put these two equations inside and they will get the values for K1 and K2 and hence the energy. But let's just see what methods we can employ if we are put in a situation where we need to solve this. Now, before I do that, I want to rewrite this in some suggestive forms which I can easily manipulate and analyze for me to get the energy values. For that, I'm going to make a substitution. Alpha is equals to K2A divided by 2. The reason why I do that is because I see there's a K2A divided by 2 and a K2A divided by 2 for both arguments of the trigonometry function. So most logically, I can substitute alpha inside there. And not only that, notice that I put an alpha n. Okay, the reason why I put an alpha n, because I know from the discussion of bound states, I will get discrete energy values. So I'll get discrete values for E, thereby giving me discrete values of K2, and thereby giving me discrete values of alpha. So the alpha subscript n is just to remind me, or remind the reader, that we're having discrete values for alpha. Okay, so now this would handle the arguments inside the trigonometry functions. Now what about the K1 and K2 outside? I anticipate that I will multiply both sides by a divided by 2, because for me to do that, when I do that, I got a K2 divided by 2, and then I can just substitute the alpha for both the K2 which is on the outside. But for the K1, I suspect also that there's a K2 encoded somewhere in the K1. Why do I say that? Because notice it's 2m potential V0 minus E. The 2m E would somehow, if I expand it, I can substitute the K2 inside. Well, let's see whether is that what we get. So K1 squared, I'll just square that, is given by this. I will divide both of the terms, or the difference of both of the terms by h bar squared, because I squared that. And there's a 2me divided by h bar squared. I know that the 2me divided by h bar squared is actually a K2 squared. So this K1 squared is given by that, and the K2 squared nicely drops out, okay, which is good. So later I can just substitute the alpha back inside. But I would very smartly multiply by a squared divided by 4. Now, I say it again because for me to handle the K1 and K2, I need to multiply both sides by a divided by 2. I'll multiply by a squared divided by 4 so I can bring an a divided by 2 inside the square. Okay, remember, I need to square root this if I want to bring it inside the square, which is what I want to do. So K1a divided by 2 square, okay, is equals to, multiply that over there, I will get ma squared V0 divided by 2h bar squared, and subtract by a K2a divided by 2 squared. Okay, and just as expected, there's a K2a divided by 2 which corresponds to alpha n, so I can just erase this and put alpha n squared. And since I know that this is a constant, because the constraints of the problem will constrain the width of the well, which is the value of A, and the potential, which is V0. So I will let R squared equals to ma squared V0 divided by 2h bar squared, and this now becomes our R squared. Okay, and finally, since this is a K1a divided by 2 squared, I will just remove the square and square root this one over here. Okay, square root this one over here. So our K1a divided by 2 is equals to that. The reason why I will do that, because very nicely, if I multiply both sides of these equations by a divided by 2, I will get K2a divided by 2 on the outside. Okay, now K2a divided by 2 becomes our alpha n. Okay, the cotangent, I will get the alpha n. Okay, and it's equals to minus what is K1a divided by 2. Remember, again, I'm multiplying both sides by a divided by 2. K1a divided by 2 is given by the square roots of r squared minus alpha n squared and close the square root. And doing the same for the boundary solution, or boundary conditions for the symmetric solution, I get these two equations over here, bringing the minus sign over there. And very nicely, now this is one of the suggestive forms that we want to use. Now I know you can use other forms of rearranging the equations, but this helps us to get the solutions quite nicely, as well as to analyze them. Now, noticing again that r squared is going to be fixed. R squared is dependent on the potential and the width of the well A. So it's going to be fixed. So really, I'm left with an equation, or I'm left with two equations with only one unknown. What is the unknown? The unknown is alpha. Why does it have a subscript n? Because I know that this unknown, when I solve it, is going to take discrete values. And I also want to say that, notice that these are two independent solutions. Both of them, both solutions to the problem, are discussing about this symmetric Hamiltonians, solutions to the problem. So really, as long as alpha obeys one of these solutions, it's the solution to the problem. So alpha n has to either obey this or this. Okay, both of them, are solutions to the problem. So how are we going to solve this? Well, very easy. Okay, our target again is to solving for the discrete energy values, right? So if I were to rearrange for En, okay, how do I do that? Well, look at here, okay, K2 is equal to the square root of 2me divided by h bar, and I know that the K2a divided by 2 is over there. So I can just rearrange, substitute the K2 inside the alpha n. Now if I do that and rearrange for the energy values, what I get is this. Okay, E is equals to 2h bar squared alpha n squared divided by ma squared. Okay, so this tells us that if I get alpha, I get the energy values. Okay, so how am I going to get alpha? Very simple. Now I know that I'm able to sketch the graph of this, and I'm able to sketch the graph of this. But this time, the x-axis is not going to be x, but now it's going to be alpha. Okay, remember, alpha is not known. So if I could sketch, let's just say y is equals to this, and y is equals to this, where the graphs intersect using your simple, solving these sort of solutions graphically, this sort of equations graphically, that is what we do. And it's nicely graphed out over here like that. Okay, now I just want to say that this is one of the very famous graphs that you see in quantum mechanics problems. Is what it is really? Well, it is this. Okay, noticing that, firstly, let's handle the one over here.